For this lesson, I'd like to discuss with you about the heat and temperature and the effects of heat. Okay, so for your understanding about heat and temperature, you have to compare them first, okay, with regards to the meaning. So heat is the quantity of energy absorbed or given off by an object. In comparison to temperature, it is the measure of hotness and coldness of an object. The heat in terms of unit used is a calorie or joule. And for the temperature, we have to use degree or Fahrenheit, and sometimes we have to use Kelvin. The instrument used for heat is a calorimeter, and for temperature, we have to use the thermometer. In terms of heat, okay, it's of course, as I've mentioned, it's measured in joules, and for the temperature, okay, it is measured in degrees. It is, for example, measured in terms of Celsius, degrees Celsius, Kelvin, Fahrenheit, okay, and sometimes we have the R or Rankine. Average kinetic energy of molecules within the material, it's being measured. Alright, so let's focus on the situation regarding heat. So heat is produced from molecules of matter that is continuously vibrate. Heat is an energy form that transfers from a body of higher temperature to another body of lower temperature. Once heat is transferred or released, it affects the internal energy of the body. Internal energy is the total energy in a body. Thus, it includes the potential energy and the kinetic energy of the molecules of or atoms in an object. Since you know already the differences between the heat and temperature, so there are measurements that you need to focus. Okay, these are the following in terms of Celsius, Fahrenheit, and Kelvin. So of course, as you can see on this in this table, that you need to get the freezing point of water, or the boiling point of water, and the temperature difference between freezing point and boiling point. Below here, or in this presentation, you're going to see here the situation regarding the degrees, convert to degrees or degrees Fahrenheit. So Celsius to Fahrenheit conversion formula. So to convert temperature in degrees Celsius to Fahrenheit, so you have to multiply by 1.8, or of course you have to uh, divide it by 9 over 5 and add 32. Example, 30 degrees Celsius multiplied by 1.8 plus 32 is equal to 86 degrees Fahrenheit. The Celsius to Kelvin formula is, of course, you have here the temperature, okay, K, so it's equal to temperature, degrees Celsius, plus 273.15, wherein the meaning of temperature degrees Celsius, okay, the T, degrees Celsius, and then the T for the temperature K for the temperature of Kelvin. So the last here is indicated that you have to convert Fahrenheit degrees to Kelvin. So you have degrees Fahrenheit minus 32. So for example, with that, okay, you have to multiply by 5 over 9 plus 273.15. That makes the equivalent or the answer for Kelvin. As I have mentioned earlier regarding the table presented, so the question is that what is the temperature difference between the freezing point and boiling point of water in each of the three temperature scales? As you can see here that in terms of the freezing point of water, of course, the Fahrenheit or degrees Fahrenheit, you'll see that it's 32, okay, for the Fahrenheit, and you have the Celsius. Okay, so you have there 0 degrees, and for the Kelvin you have 273 degrees Kelvin. In comparison, for the boiling point of water, you have the Fahrenheit 212 degrees, and for the Celsius it's 100 degrees Celsius, and for the Kelvin it's equal to 373.15 degrees Kelvin. In continuation, in this presentation, of course, the temperature versus heat energy of water, as you've learned a while ago, that the temperature, okay, and then the heat are actually different to each other. But then of course, learning is that we have to uh, combine them. Okay, that for example, the heat energy is of course depending on the source of the object that it can release the heat or the energy, but then it can also absorb or get energy, okay, from its surroundings. So that's the heat, okay, capacity of a certain or specific capacity of a certain object. In comparison to temperature is the measurement. Okay? Now, in this graph or in this situation, you're going to learn about the effect of heat energy to a certain object. Okay, the example here is the water. Okay, so as you can see, the graph. Okay, let's have, for example, the heat energy that represents for the x-axis, and the temperature for the y-axis. For its representation. Now, all of them are actually increasing. Okay, so the heat energy, it has an arrow indicating going to the right, increasing in energy or quantity. Now the temperature is also increasing in quantity, as this goes from the bottom or from the origin going to the top. Now, as you can see here also is that the changes in the phases of matter, okay, for example, from solid, liquid to gas. Okay, so for this actually are the phases of matter. So it's representing like a ladder, okay, going up, and there are arrows. Okay, so these arrows also indicates the process. Okay, for example, from solid to liquid. Okay, so it needs the warming or increasing of the heat energy. So as indicated in number 1, the temperature increases during melting. So from solid, okay, and to make it into liquid form or liquid phase, so you have to increase the heat energy. So it means also that it is melting. The heat from the object is actually getting increased. Okay, so it usually has to change, okay, from solid to liquid. Now, the number 2, as indicated here, energy is required for each phase change. Now, let's proceed or look at the liquid to gas. Okay, now to change that, okay, based on in the number 2 indication that we have to boil the water. Okay, so also, if you can see on the ladder also, so we have to increase again the heat energy. Okay, so of course it changes from liquid to gas. Okay, what's the process used? It's the boiling process. Okay, now as it increases the heat energy, it will turn into gas and of course release into the atmosphere. Now on the opposite side, going down to the ladder, as you can see here, that of course it cools down. Okay, now when it cools down, okay, so it condenses, okay, the water vapor, okay, in the air. So that's actually in number 3 as indicated. When the water warms, okay, the temperature decreases. So on number 4 also, the temperature remains the same when the object freezes. Okay, so from condensation, or it condenses, and then we have to cool it down again, decrease the temperature. Okay, now when we decrease the temperature, freezing. Okay, is, if you can see it on as looking at the ladder, okay, situation, so you can see that it's freezing now. Then we still remove more heat from the water. So of course it's indicated in number 5 that water may change directly also from the solid to gas. Okay, now This direct change from solid to gas is a speed in terms of giving a and actually increasing in the temperature, okay, of the object or the water. So I think that's the overall uh, presentation for this temperature and heat energy. So this is a normal process, and this is also the same thing that happens in other objects. Okay? So that's why in the next topic you're going to or subtopic you're going to learn about the specific heat capacity of other objects. Okay, so in continuation of explanation regarding this topic, or additionally, I'd like to inform you that in terms of the direct process of solid changing that to gas is the sublimation. So as I mentioned, okay, earlier, that it is the speed, okay, of the change. Okay, now that change actually is the effect in terms of the heat, okay, or the change increased in the temperature. So of course, it means to say that the object, or especially the solid ice, okay, like that, as mentioned or as an example earlier, that it absorbs, okay, the heat, okay, or the amount of heat that can in turn directly, okay, move from the solid to gas. So in this graph, okay, or in this table, okay, I'd like to uh, let you know that the temperature of a 200 ml heated or boiled water at a particular time was observed. Okay, so as indicated here, in terms of the time per minute, so this is from 0 to 29 minutes. So let's have the 0 first, okay, until 2. So 0 minutes, okay, and then 1 minute and 2 minutes. So the temperature changes or increases, okay, in terms of degrees Celsius. So you have in 0 minute, okay, you have 30 degrees, and then in after a minute, it has 32 degrees, and of course increases again. For 2 minutes, it has 34 degrees, and so on. As you can see that the increase in heat, okay, of course, or boiling, okay, of the water increases until it reach the temperature of 100 degrees. So the boiling point of water is at 100 degrees Celsius. So it was obtained or attained after heating and continuously heating the water up to 29 minutes. Therefore, if we have the boiling point for the water when the heat, okay, actually reached, okay, that level, then especially in terms of 100 degrees Celsius, so the water is going to boil, and then uh, we have also the term called specific heat capacity. The specific heat capacity is of a substance is the amount of energy required to raise the temperature of 1 kilogram of a substance by 1 degree Celsius. Now, substances with high heat capacities cool down slowly because they have to give off more heat, and also heat up slowly because they have to absorb more heat. Substances with low heat capacity heat up quickly and they lose their heat quickly. So you have to remember this very well. So in continuation about the specific heat capacity, you'll see here that there are examples of metals such as aluminum, iron, copper, gold, and lead with a mass of 100 grams each. They also have the same cross-sectional area and initial temperature. Each of the metal was placed on a separate block of ice. Gold melts the most ice and sinks the deepest. Second is aluminum. Third is iron. Fourth is copper, and lead is the last. This shows us that although these metals have the same mass and initial temperature, they absorbed and gave off different amounts of heat. This is because these metals have different heat capacities. These are examples of specific heat capacities of some common substances as indicated here. For example, the water. So you have here the solid, liquid, and gas, and they have specific heat capacities. Of course, you also have the ammonia, okay, ethanol, aluminum, carbon or graphite, and you have copper, gold, iron, lead, and mercury. A part of the topic regarding heat and temperature is known as thermal expansion. Thermal expansion happens in liquids and gases. Molecules of liquids vibrate faster to move farther away from each other and attract weakly to each other when heated. When cooled, the temperature or the vibrations of molecules become slower and move closer to each other. When the temperature is increased, fluids expand. On the other hand, when the temperature is reduced, the fluids contract. The increase or decrease in the temperature causes the volume of the fluids to change. This concept of expansion and contraction in fluids is not applicable to water. It behaves differently from other liquids, whether increased or reduced from 4 degrees Celsius, water expands. This is why water is densest at 4 degrees Celsius. The mass of the material is constant when it expands. Its volume increases and it becomes less dense. When cooled, the mass also remains constant, but the volume of the material reduces and it becomes more dense. So after you've learned about the specific heat capacity and the thermal expansion, of course, all of them are referring to the heat. Okay? So it's either the temperature cools down or temperatures goes up. Okay? Now, here you have to focus on another subtopic, which is known as heat transfer. So, can you give an example of or examples of heat transfer? So when there's heat loss or heat absorption, this is because of the heat transfer of the from the object, okay, or from the object or from out of the object. Now, one of the situations are the following, okay, in terms of heat transfer. Okay, first we have the so known convection. Okay, so the transfer of heat through a fluid. It can be either liquid or gas caused by molecular motion. Another heat transfer is by using the process of conduction. So this transfer the heat or electric current from one substance to another by direct contact. And the third is by radiation. So the energy that is irradiated or transmitted in the form of rays or waves or particles. So let me give you specific examples of the importance of heat transfer. As I've mentioned a while ago, we have conduction, convection, and radiation. So in terms of the importance or examples, so in the conduction, okay, you have heat transfers into the pot holder as you hold the hot cup of coffee. so we can prevent the holding of those hot objects. Okay, and of course we have the technology or other resources that can prevent, okay, the heat transfer. Okay, so it can also protect us. Now, in terms of convection, you have the heat transfers, for example, as the barista or the steams, okay, from a cold milk, okay, to make a hot cocoa. Yeah, so of course this is one of the example only, okay, under convection. Okay, so we have radiation, reheating of example, reheating of a cold cup of coffee in a microwave oven. Now, aside from those processes that I've mentioned to you that can cause heat transfer or the heat loss, so in our body we also have the same process. So as you can see in this picture, for example, there's a baby, and then there's this process of convection, there's an evaporation, there's conduction also, in radiation. So it means to say that these are absorption, okay, or at the same time the heat loss is also happening in our body. Okay, so there's a transfer of heat, or transfer of the energy. It's either the energy is going inside of us, okay, like when we are going to get more of energy, okay, especially like eating. Okay, so on the other hand, okay, there's also the other way of releasing the heat, okay, out of the body, like perspiration. Now, talking about other or some objects, okay, so there also the as mentioned earlier, that they have specific heat capacity. Now they have the ability, okay, different kinds of objects, okay, or metals or non-metals have different um, absorption, or we call it the ability to absorb the heat, okay, from the surrounding, or release the heat from the surrounding. Yeah, actually the factor that affects the heat chains is the surrounding, of course. So after learning about those terms with regards to a specific heat capacity and the heat transfer, or of course the absorption or heat and heat loss. So in science we have the measuring tool. Okay, we have the calorimeter, is an object used for calorimetry, or the actually process of measuring the heat of chemical reactions or physical changes, as well as the heat capacity. Okay, so as you can see in this picture is an example of a calorimeter. All right, so as I've mentioned to you that of course when we eat, it is one of the examples that our body absorbs heat, and we produce it. Of course, we have the um, energy, okay, that our body needs, and on the byproduct of that is the waste materials, or the including the perspiration. Now, in terms of calories, okay, or the energy that we need, okay, so we have it present in food. So scientists place the food in question in a sealed container surrounded by water and heat it until the food is completely burned off. So scientists then record the rise in water temperature to determine the number of calories in the product. So this is a way of determining the calorie of a certain food. Okay, so the calorie is the energy, okay, measured, okay, that's needed by our body. So different food, okay, or a specific kind of food have different energy or calorie. Okay. So I think you've learned a lot already about heat in terms of the effects in the surroundings, in our body, or the energy that we need. Okay, why do we need it? Okay, in terms of heat, then what are the changes that's happening when we put heat in a certain object? So there's this so-called heat specific and also heat expansion. Okay, so in terms of laboratory, so the thermometer, as I mentioned, it is a measuring tool, okay, for temperature. Okay, so there are many types of laboratory thermometers, such as differential, mechanical, logging, etc. So laboratory thermometers are progressively providing digital reading displays and are input capable to computer and software programs for logging purposes. It is very important for you to familiar about the thermometer that we used in the laboratory. So as shown in this picture, this is an example of it. Additional information about hot or cold, or of course the temperature and heat. So I'd like to let you know about these situations. Okay, number one, heat transfers from an object of higher temperature to an object of lower temperature. Okay, so this is very um, important for you to know, because the object actually absorbed heat. Okay? So as mentioned here, that heat transfers from an object of higher temperature. Okay? So if the certain object is cold, okay, and of course the transfer of heat is from the outside. Okay, so if the outside environment is warm or hot, and it will go to the object, or at the center, or where there's a cold region. Okay, so from higher temperature to an object of lower temperature. So this, aside from the information, aside from that, this is also a fact. Okay, so next, units of temperature can be provided by three different scales. Okay, so I've already explained to you, they are namely, okay, Fahrenheit, Celsius, and Kelvin. Now the third is that heat is a form of energy and is measured in joules. So it takes about 4.2 joules of heat to change 1 gram of water by 1 Celsius degree. A unit of heat is still common in the United States and is, of course, termed as the calorie. As I mentioned to you a while ago, that of course, hot surrounding will flow the heat energy to a lower temperature or heat, okay, especially of a substance or an object. So this is reflected in the second law of thermodynamics, that states that heat will always flow spontaneously, okay, from hotter substances to colder ones. So it means spontaneously. Okay, so it's continuous, okay, from hot substances to colder ones. So this is called as the second law of thermodynamics. So okay, you can look at the picture, okay, or illustration, okay, from the box or from the area with the hot concentration, and then the heat is flowing towards the cold temperature or cold area. All right, so to prove that there is a law of thermodynamics, okay, so one of an experiment or situation is presented here. Okay, I'll first like to inform you about this. Okay, so the first thing, okay, is that the ice cube dropped into a bowl of warm water gained heat. Okay, so that is thermal energy from the water into the bowl. So the second process is during the experiment is that adding thermal energy leads to an increase in the kinetic energy of the ice molecule, and thus an increase in temperature. Yeah, so I think this is general and observed, okay, if you do this. Okay, so as also I've mentioned from the entire explanation of the topic. Then the third is that furthermore, the ice will continue to gain thermal energy, causing its molecules to move faster and eventually break their intermolecular bonds or melt. So that's the reason that the ice melts, because the heat from the surrounding they actually entered into the ice. Okay, so it absorbs heat. Okay, now the temperature of the ice, of course, increases. Okay, as I already explained, of course, a while ago. Okay. Now, the last thing, again, in this experiment situation is that the temperature of the recently melted ice will increase until everything within the bowl reaches equilibrium, meaning a consistent temperature throughout. Now, when the ice melted, so there is the so-called equilibrium. So equilibrium is the equal of heat that's transferred to the ice, and it's already turned into water. Okay, so we stop there. It means to say that the experiment did not or the situation did not go beyond the process of heating it more or giving more heat to the melted or to the water, because of course, as I've mentioned, that if you heat or put more, increase the heat of the object, or of course the water, in turn it will boil, right? So it will turn into gas. All right, so I think that's everything about this topic, and I hope you've learned a lot. Okay, thank you very much.